the only constant is change, or change is the only constant, is something that you must have heard in passing. Could be in books, series, movies, or could be a philosophy teacher teaching you about this particular topic, or it could be mentioned colloquially between you and your friends. And just to put it in context, it was given by Heraclitus, who was a Greek philosopher and who later on gets name dropped by Plato. And Plato refers to the same adage and says that Heraclitus probably spoke about how nothing stays the same and everything changes. And then he goes on to interpret it further along the lines of Heraclitus that in life, a life is like a flow of river, which means that you cannot step on the same stream twice. And the whole idea here is the fact that change is the only constant, right? Now, when you start looking at Earth's history, especially through such a huge geological timescale, when we're talking about billions of years at a time, you realize that the same adage of change being the only constant in life also applies to Earth itself. As you would recall, in the last 2 episodes, we've spoken about the formation of Earth, right? We spoke about how the small ball of floating dust sort of started coalescing together, became these melted chondrules, and these chondrules further collected together to make a small planetesimal, and that planetesimal slowly with time, attracting a lot of other particles around it, became this protoplanet. Now, this protoplanet did not really stay for long before it got impacted by Theia, the other protoplanet, to create the Earth and Moon that we spoke about. And from here onwards, also, there wasn't any stability. We know how hot the Earth was initially, and then it started cooling down, but then it kept on getting bombarded by asteroids, and it kept on changing the surface chemical composition of Earth itself to a point where we suddenly had water. Right? We suddenly had water. And then looking back at the last episode and what we spoke about how life came into being, the whole idea of how life just started flourishing through random happenstance, through how random fat lipids ended up encasing themselves around certain proteins, certain amino acids, and started producing energy for themselves. Now, again, there wasn't any stability even in this case. You would find out that slowly these chemotrophs, these small organisms which loved eating chemicals, kept on going through a lot of hit and trial that Earth was experimenting with, and suddenly we had photosynthesizing microbes which started utilizing the sun's energy. Now, also, this could have been the point where stability was reached, but again, as Heraclitus pointed out, nothing stays the same, everything changes. So here we are, where in the last episode we spoke about these photosynthesizing microbes slowly terraforming the Earth itself by completely taking out the carbon dioxide that was present and creating a very oxygen rich environment, which to their own detriment completely ended up extinguishing or utilizing all the carbon dioxide that was present, killing themselves slowly in their own oxygen excreta, right? So the reason why this is so important for us is to sort of see that change being the only constant is something that can be traced back. And with that idea, I welcome you to the 3rd episode of our Itihas podcast. Now, my name is Arnab Pate, and if you're loving this podcast, make sure you drop a follow and rate the podcast wherever you're listening to. The podcast itself is available in multiple platforms. It's there on Castbox, it's there on Amazon Prime Music, as well as here where you're listening to on Spotify. Now, continuing our journey and our conversation about change, let's look at something quite amazing. I'm guessing most of us who are listening to this podcast are privy to what a globe is. A globe is this representation of Earth with all the continents and countries marked on it. Now, whichever globe you must have seen throughout your life, I'm pretty sure the position of the continents in the country have not changed. Now, I'm obviously not going to go too much in detail about the countries and the political boundaries, because those are something that is not important for us right now. That is something we will definitely talk about when we talk about modern history. But for the time being, I'm pretty sure that you are aware of the position of each and every continent and each and every ocean, and this is something that is taught to us in our initial grades and gives us our first semblance of geography, right? But think about it this way. Ever since you and I have been alive, these position of the continents have not changed, even though there has been a change. It's not like continents don't move. I'm pretty sure a lot of you must be aware about the fact that the continents are moving and drifting. Year by year, the Atlantic opens a little wider. Africa, it's slowly splitting into two, and then this whole Indian plate smashes into the Eurasian plate and is forming the Himalayas, and the Himalayas are still growing, right? That momentum is still carrying. So we are aware that these continents are moving, and yet the map of the continents and ocean has still remained the same, and that's because the timescale for you and I to be alive is so small compared to this whole geological timescale that we've been talking about, right? In this whole idea of millions and billions of years, humans have hardly been part of it for a very, very small time period. I mean, I usually give this analogy when I'm talking about the timescale of Earth, just to put it in perspective, that if I have a book with 1,000 pages, a standard book on standard font, let's say you take the dictionary itself, you would realize that you and I, in these modern times, are probably the last word or the last sentence of that last page of that book, right? So that sort of puts you into scale. So now here's the fascinating part. These continents and oceans, the way we see them today, haven't always been this way. There have always been this constant cycle of change, the constant cycle of these continents drifting apart and coming together throughout the history of Earth itself. And that is very, very fascinating for us because it helps us trace a lot of things. It helps us trace back a lot of the history that might have been forgotten if Mr. Alfred Wegener and Harry Hess hadn't proposed the whole idea of plate tectonics. Now, given that we know at what rate the continents are moving, it becomes easier to put them into these big computer models to give us a future prediction of how these continents are going to look like. But at the same time, we can ask them to trace back time, to rerun these numbers and see what Earth would have looked like 500 million years ago, or probably a billion years ago. Now, as we start going that far back, things get a little hazier. But there are other cues that scientists use to figure out what positions or what changes could have been. I'm sure most of us have heard of a compass or probably have seen one, and some of us might have been lucky enough to even hold that ancient relic in our hands, given the time and era we live in where everything is on our phones. But with this whole idea of a compass, we are aware of the fact that the Earth has its own magnetic field. Now, of special importance to us is the fossil magnetism locked into the volcanic rocks. We tend to think of our planet's magnetic field in terms of a north-south orientation, familiar from this alignment of a compass needle, but it is quite more complex than that. Magnetic field lines intersect the Earth's surface at an angle, which is known as a dip. Now, at Earth's equator, the dip is close to zero, which is nearly horizontal, but at higher latitudes, the dip becomes steeper and steeper until at poles, it is almost vertical. I'm very sure if you, at this point, pause the podcast and go ahead and Google the Earth's magnetic field, you'll be able to see those magnetic lines, how the magnetic field is dipping and going across the two magnetic poles of Earth. Now, exacting measurements of the ancient magnetic field frozen into these volcanic rocks can reveal both the north-south orientation and the latitude of the continents when those rocks solidified. And what I mean by this is that throughout a long period of time, what would have happened is most of the magnetic solids would have aligned themselves based on the Earth's overall magnetic field, and they must have been frozen solid during different volcanic activities. Now, remarkably, such subtle evidences show that some rocks now at the equator were once close to the Earth's pole and vice versa. Fossil evidence of former tropical lagoons in Antarctica and frozen tundra in equatorial Africa reinforces such findings. So, the sedimentary rock records again adds a vital data to this. Different kinds of sediments accumulate in different environments. For example, we can have the shallow seas, the continental shelves, the tundra, the glacial lakes, tidal lagoons, and swamps, each host a distinct rock type. So, you can already see that we have quite a few number of evidences to go by to sort of start mapping the changes on the Earth's surface that would have occurred some 500 to a billion years ago. Now, there's another big concept that I want us to keep in mind when we're talking about this sort of a shift in Earth's surface. It took a long time for the plate tectonics to make the original continents where we are today. At the tipping point of subduction, at the very fault line where dense slabs of Earth's earliest basaltic crust plunged down into the mantle's depth, there were some unsinkable bits of low-density granite islands which piled up one after the next to make larger and larger, stable, long-lasting landmasses. The whole idea is again of density here. We know that the Earth itself it's made up of different materials, from its core, mantle to its crust. The whole lithosphere is somehow arranged in terms of its own density. So we would find that denser material would start sinking down and lighter material will start floating up. And that's the whole idea behind this, where some unsinkable bits of low-density granite islands piled up one after the other, making larger and larger, stable, long-lasting landmasses. Now, these ancient chunks of what are now the continents go by the name craton, a term derived from Greek word for strength. And these cratons are pretty strong. Once formed, they last a long time. Now, the Earth today perhaps preserves more than 3 or so dozens of these cratons, and these cratons they can be found all across the Earth. All of these cratons began to form more than 3 billion years ago, a time before the modern style plate tectonics, when only a tiny portion of Earth's surface was dry land. So consequently, all cratons carry a precious, if somewhat wrapped and scrambled record of Earth's vibrant adolescence. And this is important for us because these cratons serve as Rosetta Stones of Earth's early history. And if you would recall, or if you have heard of what the Rosetta Stone is, you would understand the huge importance it had in us deciphering languages. Because the Rosetta Stone was a granite slab which had the same text written in 3 different languages. It had Demotic, hieroglyphics, and Greek, which ended up helping us translate and make connections between these 3 languages. So the same thing applies to cratons. The oceans can't help us decipher early Earth, thanks to the incessant conveyor belt of the plate tectonics, which produces new basaltic crust at the ocean ridges, like the Atlantic Ocean Ridge, and it swallows it up again at the convergent boundaries, the boundaries of the continents. The oldest ocean crust is not much more than 200 million years old. Anything older than that must be preserved on the continents or not at all. So keeping this in mind, you would see that these cratons are so important to us because these were those unchanging rocks from where we could collect our evidences. Now, propelled by the motion of plate tectonics, they have been shuttled about, colliding with one another to form composite cratons and supercratons, which in turn occasionally clumped into one single giant landmass, which could be called a continent or a supercontinent. Now, these supercontinents in turn drifted apart and fragmented into separate ocean-bounded island continents. Each time a continent drifted, a widening ocean formed between the diverging pieces and a telltale suit of sediments was laid down. Shallow water sandstones and limestone at first, then deep water mud and black shale. Such sedimentary sequences point to episodes of continental fragmentation. Over and over, supercontinents have been forged and then ripped asunder. It's an immense jigsaw puzzle with an unknown picture where pieces constantly change their positions and their shapes. And that is why us understanding this becomes so much more important. And according to the latest interpretations, Earth has experienced a repeated cycle of at least 5 supercontinent assemblies and breakups, extending back perhaps 3 billion years. I like how in Robert Hazan's book he writes, "No one has had the nerve to draw more than a sketch map of Earth's surface 3 billion years ago, at least not yet, but one well-vetted idea has named the first continent-sized landmass Ur, formed about 3.1 billion years ago from earlier scattered cratonic bits of what are now the South Africa, Australia, India and Madagascar." And doing a callback to the magnetic lines that we were talking about, we found through the analysis of those magnetic lines that the continent of Ur persisted for almost 3 billion years and began to split apart only about 200 million years ago. Now, the earlier true supercontinent, dubbed the Kenorland or Superia, is thought to have formed about 2.7 billion years ago from Ur and lots of other smaller pieces. Now, each time one craton collided with another, a suture zone was formed, while epic compressional forces pushed up a new mountain range. And this is something that we have always known, that mountain ranges such as the Himalayas were the suture zones of two plate tectonics coming and colliding with each other. A plethora of such features can be determined from rocks 2.7 to 2.5 billion years old, suggesting a sequential growth of the supercontinent. And similarly, the paleomagnetic data that we spoke about revealed that Kenorland was at low latitude, probably straddling the equator for most of its relatively brief existence. Now, at this point, I also want you to think that the Earth we are talking about, this Kenorland that we are talking about, the landmass that is going to be there with these very newly formed mountain ranges, they are still going to go through the rigors of erosion that we see on Earth today. We know how big mountains and rocks are eroded through the action of climatic forces, be it wind or water. So that erosion would create sediments, and these sediments would go ahead into the shallow ocean margins. Now, most early Earth modelers posit an ancient atmosphere quite different from that of today. Oxygen was totally absent during this time period, while carbon dioxide levels may have been hundreds or thousands of times greater than in our time. And again, not to confuse you with the timeline, we are still talking about around 2.5 to 2.7 billion years ago. So this landmass is forming before the great oxygenation event happened. So we can understand the kind of atmosphere that we are facing around that time. So the type of sediments or the erosion that will happen due to the high presence of carbon dioxide is going to be completely different than what we would find in an oxygen-rich environment. So the rain would have fallen as drops of carbonic acid that ate away at the land and transformed hard rock to soft clays. Rivers carried their muddy cargo into the shallow coastal slopes of the encircling oceans, where thick delta-like wedges of soft sediments accumulated. So by about 2.4 billion years ago, about the same time that oxygen began to accumulate in the atmosphere, Kenorland experienced the flip side of the supercontinent formation. Geomagnetic data reveal that the divergence of Ur from other cratons as Kenorland began its protracted fragmentation started happening. Those cratonic puzzles, they started scattering from the equator towards the pole. Newly opened shallow seas between the diverging pieces led to thick deposits of shallow marine sediments, and the supercontinent cycle thus began. Following this, the next supercontinent episode, one more sharply in focus than Kenorland, thanks to the younger and much better preserved suits of rocks, began about 2 billion years ago, at a time when Earth boasted at least 5 separate supercontinent-sized landmasses. Largest among these was the Laurentian supercraton, a conglomeration of at least half a dozen cratons thousands of miles across, and that encompasses much of what is now the central and eastern North America. And if you remember, the original continent Ur that we spoke about, it soldiered on as the second largest landmass, separated from Laurentia by a substantial ocean. Now, the much smaller Baltica and Ukrainian cratons, which form the core of what is now the Eastern Europe, and the cratons representing parts of what are now South America, China and Africa, were also large islands approaching the continent size. Now, by the time we roll into the Proterozoic Aeon, when the Earth is about 1.9 billion years old, we find that these varied land masses have collided at convergent plate boundaries, causing new mountains to rise and forming a supercontinent variously named Columbia, Nina, Nuna, or Hudson Land. Now, this vast barren land, roughly estimated to have been around 8,000 miles long from north to south and 3,000 miles wide, incorporated almost all of Earth's continental crust. Now, here I want you to think about something. When you have such a huge landmass, which is surrounded by oceans, you would realize that not a lot of moisture will reach towards the inner lands. So what you would have would be an interior which was very hot, almost like a desiccated terrain with absolutely no vegetation and great expanses of rusty desert. And if you see this from space, you would find a strangely lopsided world with its one great enreddened landmass surrounded by an even more expansive blue superocean. So, the equatorial Colombian supercontinent is the supposed starting point of what is known as the dullest period on the Earth's lifetime, something that we often know as the boring billion, or that time period from 1.8 billion years to about 850 million years ago. And yet, like we have been talking about since the very beginning of this podcast, we know that nothing really stays the same, right? I mean, from what we've noticed so far, we know that the oceans, the atmosphere, the surface, the deep interior, the geosphere, biosphere, everything has been subject to change over the eons. So to think that the Earth would have had a billion years without any dramatic events, with no significant transition in the near-surface environment, with no great novelty in the living or the non-living world, it would literally mean that there was some sort of a perfect harmonious balance going on for a billion years. Which could be remarkable if it was true. But it isn't. And the biggest reason behind all of this is the presence of plate tectonics. See, the plate tectonics never stopped. A notable feature of supercontinents is that they continue to grow gradually at the edges as ocean plates plunge under their margins and new volcanoes rise near the coasts. The modern-day expansion of the Pacific Northwest coast, where such majestic volcanoes as the Mount Rainier, Mount Hood, Mount Olympia are still active, is but one recent example of this age-old phenomenon. So, this expansion of this Columbia supercontinent was still happening. Now, even more continental crust was added to the Earth's inventory when Columbia experienced episodic rifting and breakup into smaller continents and islands. About 1.6 billion years ago, the beginning of the period known as the Mesoproterozoic, the splitting off of the continent Ur to the west from Laurentia and the rest of the Columbia to the east led to a major intercratonic sea and the deposition of massive sedimentary sequence reaching thickness of more than 10 miles. Now, this rifting of Columbia into two diverging landmasses had other consequences as well. See, the Laurentia, Ur and other continents were still all centered more or less about the equator, which means that there was still no continent at the poles. Now, if there are no continents at the poles, there is going to be no ice build-up at the poles. Now, I want you to put a pin on that. See, whenever we speak about global warming, one of the biggest concerns around it has been the fact that if the global temperature rises than what it is supposed to be on an average, it would result into the melting of the polar ice caps that we have. And if the polar ice caps melt, the average water level all around the globe will rise. And the problem with that is, as you can imagine, if the water level rises all around the globe, there are going to be so many coastal cities and coastal countries and areas which will go underwater, which is obviously a threat. But in our case, in our discussion of there being no landmass on the poles and hence having no ice caps on the poles, it basically tells you that during this time period, the water levels are already very, very high. Now, we did have shallow seas in the vast swaths of Laurentia's new west coast. Likely less than a quarter of the Earth's surface was dry. And for a time perhaps exceeding 200 million years, Earth's total land area was dramatically reduced, while thick sedimentary deposits were accumulating in shallow waters around the globe. Now, no ice also means no glaciers. We have to keep that in mind. The interval from 1.6 to 1.4 billion years ago holds none of the characteristic glacial remains, piles of ice-rounded cobbles or boulders and sand and gravel that are found in most other geological ages. None of them are found during this Mesoproterozoic period. And yet, because of all these tectonic changes, it turns out this period wasn't as boring as we thought it would be. And here comes the kicker. The boring billions saw the formation of not one but two supercontinents. The scattered fragments of Columbia drifted apart for perhaps around 200 million years or so, but a continent landmass as big as Columbia could drift about without converging for so long, right? So what we have is about 1.2 billion years ago, Ur, Laurentia and other Mesoproterozoic continents began to reassemble into a new landmass called Rodinia. Now the exact geography of Rodinia is still under debate, but from the geological and paleomagnetic data that we have gathered, we could make a small outline, and based on that we could see that the entire supercontinent was situated near equator, with Laurentia, what is now most of North America, at the center, and large pieces of all other continents stuck on its north, south, east and west. According to several reconstructions, you will find that Baltica and chunks of what are now Brazil and West Africa lay to the southeast, with other pieces of South America to the south and fragments of Africa to the southwest, though the details of relative position of Australia, Antarctica, Siberia and China are still sort of unsettled. Now, the biggest distinguishing characteristic of Rodinia is its absence of certain kinds of rocks. Unlike any other interval for the past 3 billion years, few, if any, sedimentary deposits have been preserved for the period between 1.1 billion and 850 million years ago. And this whole idea of there being no sedimentary deposits points to this amazing thing, that this hiatus from 1.1 billion to 850 million years ago had no shallow seas between the continents. Because there were no shallow seas, there were no sedimentary deposits, which basically means that most of these continents fit together neatly. Nor does it appear that there were any large inland seas of the kind that once flooded all of central North America and laid the sedimentary foundation for the Great Plains some 100 million years ago. So, from all of this, we know that in spite of the meager rock records near its end, the great time interval from 1.85 billion to 850 million years ago witnessed many notable changes as a consequence of this cratonic dance of these continents rifting and coming together. Two supercontinents were assembled during this boring billion, each producing a dozen mountain ranges by cratonic collisions. And in between those two gatherings of the lands, as the Columbian supercontinent drifted apart, some of Earth's most impressive sedimentary sequences were laid down. Much of Earth's land was submerged and then became dry again. The rate of sedimentation varied by the orders of magnitude. Ice caps disappeared and reappeared, and that's a lot of changes for a time period known as the boring billions. And then there is the flip side of the same coin. If we have such a huge landmass, we will also have a huge globe-encompassing superocean, which has been named Mirovia. Now let's put all of this into perspective. We know about the Great Oxidation Event. We know that it lasted from 2.4 to 1.8 billion years ago. And during this period, we know that the Earth went through a time of primarily atmospheric chemistry changes. Earth's atmosphere transformed from essentially having no oxygen to having a percent or two, and that's a monumental change as far as the near surface environment goes. But to Earth's ocean, the big changes were yet to occur. Now, prior to 2.4 billion years ago, the oceans were rich in dissolved iron, as we had spoken about earlier, a state that could be maintained only if the water column was utterly devoid of oxidants, and also low in sulfur. With the atmospheric changes of the Great Oxidation Event, some of that iron was removed as iron oxides in shallow water, either directly by the oxygen or indirectly by reactions with oxidized weathering products from the land. Now, oxygen in the atmosphere also led to the rapid weathering and erosion of sulfur-bearing minerals which flowed into the ocean and consumed more iron. These chemical changes triggered a massive deposition of banded iron formations, and these banded iron formations, or BIFs, are the thick ocean floor sediments with layer upon colorful layers of iron minerals that now constitute most of the world's iron ores. Now, these banded iron formations making process was gradual, and the oceans held a lot of iron. So the banded iron formations, the depositions from these continued for another 600 million years. By the time of the boring billion, the oceans were still anoxic, but they had most of their dissolved iron. Fast forward a billion years, photosynthetic algae that we have already spoken about, they continued to produce oxygen, which began to take over the oceans, and by 600 million years ago, most of Earth's oceans were oxygen-rich, top to bottom, and what happened in between is the crux of boring billion. And this time period is known as the period of the intermediate ocean. So this 600 years from where we went from having nearly zero oxygen to having a completely oxygen-saturated ocean is what we're going to talk about. Now, the Great Oxidation event produced enough oxygen to influence the distribution of any redox-sensitive elements, including iron, but not nearly enough to oxygenate the oceans. On the other hand, enhanced weathering and oxidation of the land introduced lots of sulfate into the ocean. Hence, the intermediate ocean became enriched in sulfur, while it was poor in oxygen and iron, a steady state that persisted for a billion years. Now, this protracted anoxic sulfide intermediate ocean was both good news and bad news for life. On the plus side, the influx of sulfate provided an excellent energy source for some microbes. They made their living by reducing sulfates to sulfides. Hints from the fossil records, including distinctive molecular biomarkers, sulfur isotope data, and even small, well-preserved microbes in chert, all point to a thriving Mesoproterozoic coastal population of green and purple sulfur bacteria. Now, these sulfur-eating microbes, which persist today in some anoxic environments, produce organic sulfur compounds that smell just awful, like tragically failed septic systems. And I like this really amazing comment by Linda Carr. Linda Carr was one of the most pioneering researchers of this Mesoproterozoic period, and she mentions that this whole period would have been very, very smelly. And it makes sense with all the sulfides going around. Now, the bad news for life was its reliance on nitrogen. This nitrogen gas is abundant, constituting 80% of today's atmosphere. The problem is that life's biochemistry cannot use nitrogen gas. Instead, life requires nitrogen in its reduced form called ammonia. And would you look at that? Life has evolved a clever protein, an enzyme called nitrogenase, that converts nitrogen to ammonia. But there's a catch. This nitrogenase enzyme relies on a cluster of atoms containing sulfur plus a metal, either iron or molybdenum, but neither metal was present in the intermediate ocean. The iron had been removed during the formation of these banded iron formations, so that wasn't an option. And molybdenum, on the other hand, is soluble only in oxygen-rich water, as in today's oceans. During the anoxic time of the intermediate ocean, molybdenum was to be found only near weathering coastlines in relatively shallow waters, where we suspect these sulfur-loving bacteria would have thrived. So what does all of this mean? It means that the intermediate ocean harbored microbial life, but such life could thrive only near the coasts. Sulfur-reducing bacteria coexisted with oxygen-producing algae, and for a billion years, life hung on, but there were few biological innovations. Now, here is something that I never really paid heed to before actually researching for this particular podcast. I remember reading Robert M. Hassan's book and also reading his article on mineral evolution. And that particular article had this amazing line of thought. It spoke about how minerals would have developed on Earth. Now, previously, it was believed in the great study of mineralogy that the biosphere doesn't really contribute much to how the minerals are formed. But planet progresses from mineralogical simplicity to complexity, and from only about a dozen minerals in the dust and gas that made our solar system, we somehow went to more than 4,500 known mineral species on Earth today. And the kicker being, 2/3 of which could not have existed in a non-living world. So the main question surrounding this was the fact that if we have different forms of mineral of a particular element, then it is important for us to ask, when did they first appear? What process led to their diversification? Have any of these minerals become extinct? And no one has ever tried to answer such questions because it's hard enough to catalog every mineral of a given element, but to tease out when each species first appeared or disappeared was a monumental task. Now, my further reading into these researchers gave me a few pointers. Initially, I thought that the Great Oxygenation event, which started from 2.4 billion years ago, would have had a major impact on how these minerals were developing. But turns out, it was actually during the boring billions, during the formation of Kenorland, during the formation of Colombia, is when these minerals ended up forming. And yet, a big mystery comes in when we see that the same process is not repeated during the formation of Rodinia. So, at this point, these questions are there, but the answers aren't really clear. To think that the explosion of new minerals was a consequence of the supercontinent cycle, and it being a signature phenomena of the boring billions wasn't really true. And could it have been a delayed reaction to the rise of oxygen? And what about certain elements like mercury, where the formation of mercury sulfides into cinnabar was restricted by these sulfide-rich waters that we spoke about earlier? So all of these things, this poorly documented interval between 1.85 billion to 850 million years ago shares these inexorable processes of change that have characterized every stage of our planet's evolution, and yet we don't really have answers to these mineral formations. Which is okay, because as we now go on from here, by 850 million years ago, Earth's near-surface environment had changed irreversibly. The increasing oxygen content, the oxygenated ocean, the margins teemed with algae and other microorganisms, including the stinky sulfur bacteria, while the lands were poised to burst with new life. If nothing else, the mysterious, not-so-boring billion teaches us that the Earth has the potential to settle into a stasis, a benign balance of its many competitive forces, but these again weren't really static periods of nothing happening. Gravity and heat flow, sulfur and oxygen, water and life can find and maintain a stable equilibrium for hundreds of millions of years. But there's always a but. Give any of these forces a nudge and the Earth can become unstable, unbalanced, reaching a tipping point with consequences difficult to anticipate. Consequences so large that they can disrupt the near-surface environment in matter of years. And this is exactly what happens next. And that is exactly what we are going to discuss in our next podcast. So again, thank you so much for listening. Thank you so much for sitting through this. I hope it's not very complicated. If there are any things that you want to research further or any questions you want to ask me, you can reach out to me on my email ID that will be provided in the description of this podcast itself. Again, if you're liking this podcast, make sure you follow and share it with any of your friends who are interested in our deep dive into history. Don't worry, I'm not going to take a lot more time in the geological timescale, though we will take our sweet time when we reach the Jurassic and Triassic periods, because come on, dinosaurs are cool. And other than that, we will slowly be going through this whole geological timescale and reaching the point where evolution takes a turn, where chimpanzees turn into human, and that would be very interesting to see. So again, stay tuned. This is Anapati. You're watching the Itihas podcast of Indian history and history in general, and thank you so much for being interested, and I'll see you in the next podcast. Bye-bye.